For most of human history, we thought we lived at the center of everything. Not the center of a country or a continent or even a planet, but the center of the entire universe. Every star was part of our cosmic home. Every point of light belonged to us. The Milky Way wasn't a galaxy. It was all of existence. And then something impossible appeared. At the edge of early photographic plates, faint, fuzzy, spiraling shapes, objects that looked like galaxies but couldn't be because galaxies weren't supposed to exist. These spirals were too strange, too symmetrical, too far away, and too bright to fit inside the universe we thought we understood. And yet there they were, tiny whirlpools of stars, quietly mocking the idea that the Milky Way was the whole of creation. No one could explain them. No one could agree on what they were. And for nearly half a century, the scientific world tore itself apart, trying to decide whether these ghostly swirls were small clouds floating inside our galaxy, or entire island universes, many times larger than the Milky Way itself. What came next was the moment the universe broke open. One night, high in a cold observatory on a mountain, Edwin Hubble aimed a telescope at a single spiral nebula and caught something no one had ever seen before. A star blinking with perfect regularity, a Cepheid variable so far away that its light had been traveling for more than 2 million years. That single pulse shattered the old universe. It proved, with quiet, mathematical certainty, that the Milky Way was not everything. It wasn't even close. Our galaxy was just one swirl among billions, floating in a cosmic ocean so large that the old idea of everything became laughably small. And that was only the beginning. Because once the boundary broke, once humanity accepted that we were not the center, not the whole, not even a noticeable fraction, a flood of new discoveries followed, galaxies gathering into clusters, clusters weaving into superclusters, superclusters stretching into vast filaments held together by dark matter, and beyond those filaments, the realization that the observable universe itself spans 93 billion light-years, yet still might be nothing more than a tiny bubble inside a much larger, hidden whole. This is the story of how the universe suddenly expanded beneath our feet, how a handful of mysterious spirals unlocked a cosmos beyond imagining, and how a single star in a distant galaxy forced us to redraw the edges of reality. The question started small, a faint spiral smear on a photographic plate. Soft, grainy, almost an error. How could that threaten the universe we thought we knew? If every star belonged to a single, all-encompassing Milky Way, then these spirals had to be minor. A quirk of gas, a cloud in the foreground, harmless. Yet that little spiral sat there, refusing to fit. By the early 1900s, astronomers had piled up lists of these objects. The catalogs gave them names and numbers, but not certainty. They were called spiral nebulae because that's what they looked like. Structured pinwheels with curled arms and bright centers. That structure was the problem. Typical nebulae blurred into diffuse glows, ill-defined and amorphous. These spirals were tidy. They had patterns on glass plates. Long exposures pulled out delicate arms and central bulges that did not behave like simple clouds of gas. The more plates collected, the stranger the pattern looked. It was not one oddball object. It was a class. The confusion cut to scale. If the spirals were small, they might be within the Milky Way, minor features sprinkled through our own star system. If they were large, really large, they might be outside the Milky Way altogether. That second option carried a cost. It would mean the Milky Way was not the whole of existence. The universe would suddenly be larger than anyone had measured, or even prepared to measure. The meaning of everything would lose its edges. Early plates did not answer the question. They raised it. Long exposures showed arms so thin they looked carved, with mottled knots along the swirl suggestive of star clusters. The cores glowed sharply, more like the centers of star systems than the hearts of wispy gas. The shapes repeated across targets. One spiral's arms wound tighter, another opened wider. Some showed dark lanes cutting across the light like absent ribbons. What kind of cloud arranged itself in spirals with a bold, bright center? The photographs refused the easy label. Spectra added another layer. When astronomers split the light from some spirals, they saw hints of motion. Lines shifted in ways that suggested rotation. A gas cloud could rotate, but the measured behavior signaled heft. Mass. Something with enough gravity to sustain orderly spin on a large scale. Those early spectral observations did not settle distances, but they chipped away at the idea that these were simple, local wisps. The data pointed to systems, not smudges. Yet almost everything about the larger cosmos was uncertain. Distance measures were scarce and fragile. Parallax worked only for relatively nearby stars. Beyond that, estimates leaned on assumptions. Brightness standards that might not be standard, populations that might be mixed, and methods that stacked guess upon guess star counts across the Milky Way varied by orders of magnitude depending on how one corrected for interstellar dust. Even the size of the Milky Way was up for argument. In that fog, the spirals sat just beyond reach, mocking the tools aimed at them. The prevailing view made caution seem wise. If the Milky Way filled the universe, then spirals had to fit inside it. That was the default, and defying. The default wasn't simply a technical adjustment. It would shift the center of meaning. If there were other great star systems out there, the Milky Way would become one among many ordinary. That word weighed on people. It was not only about data, it was about identity. The thought that our galaxy might be typical, not supreme, pressed on the pride that had survived previous demotions. Astronomers argued from the evidence they trusted. Some looked at novae recorded in spirals. If these outbursts matched novae in the Milky Way, then their apparent brightness would imply a distance. But those comparisons were risky. Classification was muddy. A bright point in a spiral might not be the same event as a familiar nova in our neighborhood. Mislabel one and the yardstick bends. Others leaned on counts of faint stars in the spiral's halos. If those were individual stars, the spirals were nearby. If they were unresolved clusters, the spirals might be far away. The plates had limits. Grain and blur left room for interpretations to diverge. The community watched the evidence stack unevenly. Spectra whispered of rotation and mass. Photographs showed organized structure. Distance methods hung in midair. Every conference and paper built a little more tension. The lists of spirals grew. The labels persisted. But the meaning slipped. If a spiral's rotation hinted at a massive system, then the Milky Way stopped being a container and became a pier. That conclusion carried emotional friction. Admitting other galaxies meant our home was not the universe. It was an address in a larger city. Observers tried workarounds, longer exposures, better plates, more careful calibrations. They returned with spirals that revealed themselves more deeply and refused to resolve the central question. The arms were not artifacts. The cores were not tricks. The patterns were real. They simply did not tell you how far away they were. A spiral that sits close can look identical to a spiral that sits far away if you do not know its intrinsic size. The sky offered shapes without scales. This stalemate fostered a sense of suspense that felt like a tightening knot. Even those who favored a single galaxy universe knew the spirals demanded an explanation. They could not be folded into existing categories without strain. Those who leaned toward the island universe's view recognized they needed a clean distance, something solid. Without a ruler, both sides could keep circling the same arguments. The debate sharpened, and with it, the stakes. The catalogs played a quiet role in hardening the lines. With so many spirals recorded, the phenomenon was no longer rare. A handful of odd cases could be dismissed, hundreds could not. Each new entry added weight to the need for a coherent story. The photographs provided the same unsettling pattern over and over: a central bulge, two or more winding arms, often with dark streaks suggesting dust. Those details matched some features seen in the Milky Way when viewed through intervening material. But an internal analogy still lacked proof it was a guess, not a measurement. Spectral observations kept nudging the conversation toward mass. Rotation in some spirals hinted that large amounts of matter were moving in organized ways. Red shifts in others suggested recession, though interpreting those shifts without a robust model of cosmic expansion left ambiguity. Still, the numbers didn't sit well with the idea of tiny, local clouds. They signaled structure on a scale that competed with the Milky Way's own bulk. If that were true, then those spirals were not residents inside our house. They were neighbors down the street. Outside the technical arguments, there was a psychological edge. Becoming ordinary is not painless. Scientists pride themselves on following evidence, but they are also people embedded in cultures and traditions. For decades, students learned that the Milky Way was the universe. Textbooks, talks, and popular accounts repeated it as a given. To reverse that would mean rewriting fundamental statements, not only in journals, but in the minds of the public. People had just begun to absorb that Earth was not central in the solar system, and that the Sun was not central in the Milky Way. Now, perhaps, the Milky Way itself was not central in the cosmos. Each move outward brought a fresh round of discomfort. The dispute picked up public momentum. Lectures framed the question starkly: are the spirals small and near, or vast and far? Newspapers summarized the sides, compressing nuances into headlines. The stage was set for a formal clash. Two prominent voices would present the best cases that could be assembled from the photographic plates, the spectral data, the star counts, and the few distance clues available. It was not theater for its own sake. It was an attempt to organize uncertainty, to show where the evidence leaned and where it failed to reach. Researchers knew the holes in their methods. Distance was the Achilles heel. Standard candles lacked trustworthy calibration. At the scales required atmospheric limits blurred the faintest details. Interstellar dust dimmed and reddened light, confusing brightness-based estimates. The result was a scientific landscape where two incompatible maps could both claim plausibility. You could read the same photographs as proof of proximity or as signs of grandeur, depending on the assumptions you carried to the eyepiece. Tension built not because people loved conflict, but because the question mattered. If the spirals were external galaxies, then the universe's size ballooned by factors that strained imagination. If they were internal curiosities, then the Milky Way remained the whole, with the spirals as ornate clouds swirling in our own backyard. Either way, the answer would reshape how astronomers set priorities, built instruments, and interpreted every future observation. As the meeting approached, both camps came armed with numbers, diagrams, and carefully chosen examples. They highlighted novae brightness, globular cluster distributions, dark lanes and spirals, and the displacement of our Sun from the Milky Way's center. Each piece carried implications. None delivered finality. That was the discomfort and the draw. The evidence was impressive and incomplete. It supported sharp claims and left room for doubt. The night the sky hesitated is less about a single evening than about a stretch of years when instruments showed more than interpretations could hold. Photographic plates had outpaced certainty. Spirals had become familiar, and familiarity had made them more disruptive, not less. They refused to collapse back into nebulae, in the old sense, and they refused to step forward as galaxies without a decisive measurement. So the community did what communities do when a question grows larger than private correspondence and scattered papers. It scheduled a confrontation. A formal debate would place the competing pictures side by side, force clarity in the framing, and test how the arguments survived direct scrutiny. People arrived with confidence and with gaps. They spoke to audiences far beyond the room, aware that the outcome would frame teaching and research for years. At that point, the sky still held its breath. The photographs were uneasy, the spectra were suggestive. The distances were slippery. The Milky Way, assumed to be the universe, stood as a claim waiting for a verdict. The emotional weight sat in the background, shaping how the stakes felt even as the speakers stuck to data. The spirals had forced a hard question onto the stage. What followed was the great debate forming on the horizon, both sides certain enough to argue, each side aware that the evidence had seams, and out beyond the words, the plates kept filling with spirals. From unease on glass to arguments in public, the path tightened toward a showdown over the size of everything. Why would two respected astronomers argue over the very size of reality? Because both could point to real data, and the data tugged in opposite directions. In 1920, the Smithsonian Museum of Natural History hosted a formal debate between Harlow Shapley and Heber Curtis. Each carried a coherent, testable view of the cosmos. The stage lights were academic, not theatrical, but the stakes were enormous. If the Milky Way filled the universe, distances were modest and the spiral nebulae were small local structures. If the spirals were separate galaxies, then the universe extended far beyond any chart humanity had drawn. Both men thought the numbers backed them up. Neither had a reliable distance ruler. That absence made confidence dangerous and the arguments unusually sharp. Shapley's setup leaned on his work with globular clusters. These dense, ancient star swarms form a halo around the Milky Way. They are not scattered at random. Their distribution seemed to mark a center far from the sun, shifting our position away from the middle. Shapley inferred a very large Milky Way to fit the map he saw, far larger than previous estimates. With such a vast system, he argued, the spiral nebulae could live inside it as comparatively small objects. That reading kept everything under one roof and wrapped the spirals into a single grand galaxy. It answered one anxiety of the era. If the spirals were internal, then the universe remained a single household, not a collection of cities. Curtis arrived with a different reading of the same sky. He favored a smaller Milky Way and a much larger universe. He pointed to the dark lanes that cut across spirals, features that resembled dust obscuration on galactic scales rather than in local clouds. He emphasized the counts and brightnesses of novae seen in spirals, which seemed too bright and too numerous if the objects were nearby. If those eruptions were as luminous as they appeared, the spiral nebulae had to sit far beyond the Milky Way, making them entire island universes. In his accounting, the sky contained many galaxies, and our Milky Way was one member of a larger population. Between them lay conflicting distance estimates. No one yet had a ladder sturdy enough to climb out to the spirals. Parallax reached only the nearest stars. Standard candles were not standardized. Different assumptions produced different mileages. Both men built frameworks from the pieces at hand. Cluster positions, variable stars with uncertain calibrations, novae whose true brightness was not yet pinned down. Each dataset was a clue, but none was decisive. When you add up clues with unknown offsets, you can land on different answers and defend them with charts and careful language. Shapley's case drew strength from geometry. Globular clusters do not all surround the sun. They cluster around a point toward the constellation Sagittarius if that point marks the galactic center. And if the sun sits far from it, the Milky Way must be far larger than earlier maps suggested. The shift moved humanity's address off-center and demanded an extended disk thick with stars and dust. In such a large system, spirals could be satellites or interior formations, perhaps stirred up gas and stars, not external behemoths. This view kept coherence with his measurements and placed the Sun in a humbler neighborhood. Curtis's case leaned on brightness logic. If a nova explodes in a nearby cloud within the Milky Way, its apparent brightness should match novae seen in our galaxy. But the outbursts in spirals looked different. They appeared brighter than expected if the spirals were local. That implied greater distance and greater scale for the spirals themselves. He also noted the structure within spirals, central bulges and sweeping arms with dust lanes, consistent with systems as large as the Milky Way, not scraps inside it. To Curtis, the counts of novae and their intensities formed a pattern that made sense only if these were external galaxies. Complicating everything was one event in Andromeda decades earlier. In 1885, observers recorded a dramatic brightening, later called S Andromedae. It was labeled a nova, not a supernova. That classification mattered. If it had been recognized as a supernova, its enormous luminosity would have shouted distance. The misclassification blurred the scale. It made Andromeda seem more compatible with a nearby object hosting an unusually bright nova, rather than a remote galaxy with a truly colossal explosion. That single label nudged arguments in the direction of a smaller universe, or at least left the door open wide. The distance ladder was more hope than hardware. Without a robust set of standard candles calibrated across space, astronomers stitched together steps that did not quite line up. The period and luminosity of variable stars held promise, but the absolute scale was uncertain. Which variables were you seeing? How bright were they truly? Were you mixing types with different intrinsic luminosities? Errors in one step multiplied into the next, and by the time you tried to reach a spiral, the uncertainty could dominate the conclusion. That fog allowed both worldviews to walk side by side, each supported by numbers, each vulnerable to small shifts in assumed values. During the debate, both astronomers stayed close to their evidence. Shapley emphasized the asymmetrical spread of globular clusters and the Sun's displacement, reinforcing his oversized Milky Way. A single galaxy, broadened far beyond old boundaries, could absorb the spirals without breaking. Curtis pressed the apparent brilliance of novae and spirals, their statistics, and the structural features that looked galactic in scale. The presentations did not resolve the contradictions, they put them in public. You could exit the hall convinced either that the universe was one vast galaxy, or that it was an archipelago of many. The tension was not only technical. Underneath ran a current about human placement. A single, enormous Milky Way offered a universe that was expanded but still singular. Many galaxies offered a universe of neighborhoods, with ours unexceptional. That shift in status carried emotional weight. If spirals were external, then the Milky Way's grandeur was no longer the ceiling of the cosmos. The mental map would have to expand, and with it, the sense of what counted as normal. But the debate could not decide status by philosophy. It needed distances that held up to scrutiny. After the event, journals carried analysis and counter-analysis. Observers collected more plates of spirals, noting dark lanes and occasional outbursts. Spectra showed rotation in some spirals, a hint that mass, not mere gas wisps, held them together. Still, without a calibrated yardstick, those lines and smudges remained open to interpretation. You could plug the measurements into either framework and get a defensible narrative. That is the fertile but frustrating terrain of science before a clean measurement lands. Models multiply, and a single assumption can sway the balance. The Andromeda outburst kept echoing. If the 1885 event had been interpreted as a supernova, the implied luminosity would have stretched Andromeda outward, but with the nova label, it sat comfortably in both camps. It looked like a bright event in a perhaps not too distant object. That ambiguity fed into Curtis's brightness argument, but it also allowed skeptics to say the data did not demand extragalactic distances. In a field starved for anchors, classification drift mattered. A word on a page could tilt the perceived size of the sky. The audience of peers understood the limits. They knew parallax ended close by. They knew spectra gave velocities but did not give independent distances unless anchored. They knew variability held promise, but calibrations were still being hammered out. The debate's value was to lay these known unknowns bare and to draw clear lines for what kind of evidence would settle the matter. Both sides pointed toward the same key. Find a reliable distance to a spiral. That meant a standard candle inside a spiral, one whose intrinsic brightness could be trusted. In that sense, the event was less a verdict and more a checklist. What would count as decisive? A variable star with a well-known period luminosity relationship, seen and measured inside a spiral A, consistent calibration for that relationship, checked against closer systems. A method for confirming that what you saw in a spiral matched the same class of star. Used for the calibration, the community could agree on the path, even if they could not yet walk it. The missing tool was not a telescope, but a ruler woven into starlight. By the end, no one left with a knockout. The cosmos remained undecided, suspended between one galaxy vast enough to hold everything and a universe spread across countless galaxies. But a direction had emerged. The arguments had clarified where the leverage would come from, better distance measures tied to dependable standard candles. That is why the next step did not look like a fight. It looked like quiet, careful work in photographic rooms and on mountain summits, scanning plates for a specific kind of heartbeat. Henrietta Swan-Leavitt had already placed an essential piece on the board with her study of Cepheid variables. She found a relation between how fast they pulsate and how luminous they are. The concept was simple and powerful. If you could time the pulse, you could know the true brightness. If you knew the true brightness, you could compute the distance. During the debate, that tool was not yet fully calibrated for the distances in question. But it existed, and it promised a way to move beyond inference from novae and cluster distributions. What the field needed next was to wield that rule inside a spiral. Find a Cepheid in a spiral nebula. Measure its period with patience and precision. Compare the measured brightness to the brightness it must have at that period. The gap would be the distance. No more piling assumptions on ambiguous events. No more treating the entire Milky Way as stretchable to fit the argument. A star would tell you how far away it was. That would, in turn, tell you whether the spiral housed it as a neighbor or stood far away as a separate galaxy. The great debate, then, did something vital. It drew the borders of uncertainty and pointed toward the kind of observation that could erase them. Both astronomers were right to insist on evidence. Both were constrained by tools not yet sharp enough. They argued over the size of reality because reality had withheld its measuring stick. When that stick became available, the question would shrink from philosophy to arithmetic. The audience did not know exactly when that would happen, but they knew what to look for. A star with a clock built into its light. Enter Henrietta Leavitt's discovery as the quiet rule that would let astronomers weigh the distances they needed. Her relation stood ready to transform a blinking star into a number on a line. All it required was a clear target and the patience to follow the rhythm until the math clicked into place. How can a single star's heartbeat weigh galaxies? By turning time into light, and light into distance. Henrietta Swan-Leavitt found that certain stars do not shine steadily, they pulse. Their brightness grows and fades with a rhythm that is not random. She worked with photographic plates of the Magellanic Clouds, where thousands of stars lie roughly at the same distance from Earth. That meant differences in their apparent brightness came mostly from their intrinsic power, not because some were closer and some farther. Among them, she identified a class of variables, Cepheids, whose periods were linked to how luminous they truly are. The longer the cycle, the brighter the star must be. With that simple relation, a clock in a star became a clue to its wattage. The relation looked clean, but it needed an anchor. A rhythm to luminosity link still lacked an absolute scale. Without knowing the true brightness of at least one Cepheid from geometry, every distance would float. Calibration was the missing step. Astronomers needed a direct yardstick, parallax, for a nearby Cepheid to pin the 0 point. Early instruments could not measure parallax for many Cepheids with precision, so estimates varied. Some adopted indirect paths, using clusters with known distances or statistical methods that introduced bias. Even so, the relation held firm across samples. Period predicts intrinsic brightness. Set the 0 correctly, and distances fall out of the math. Here is how the method works in practice. First, you monitor a Cepheid night after night and record its brightness with a consistent system. You measure the period, the time from one peak to the next. Using the period-luminosity relation, you infer the star's absolute magnitude, which is its true brightness as if placed at a standard distance. Then you compare that to what you see from Earth, the apparent magnitude. The difference gives the distance modulus, which translates directly into how far away the star is. Airglow, dust, and instrumental quirks try to nudge the numbers so observers correct for extinction and ensure the light curve is well sampled. With careful work, a single pulsation period turns into a measured span across space. This approach built the first strong rung on the distance ladder. Before Leavitt's insight, parallax worked only for nearby stars. Beyond a few hundred light-years, angles grew too small for reliable measurement with early telescopes. Cepheids extended reach by orders of magnitude. A bright Cepheid could be measured in a distant star cluster, in the Milky Way's far side, or even in another galaxy if the telescope had enough aperture and the plate had enough sensitivity. Each new Cepheid pinned a point on the map, allowing other indicators to be calibrated against it. Type Ia supernovae, for example, would later inherit their scales from galaxies whose distances started with Cepheids. The method turned blinking stars into yardsticks, and those yardsticks made a framework for everything farther out. Henrietta's relation also reshaped the map of our own galaxy. Harlow Shapley used Cepheids in globular clusters to trace where those clusters gather in the sky. Their distances implied a great congregation toward Sagittarius, not around the Sun. The Milky Way's center lay far from us, and our star was offset, not in the middle. That shift came from a practical tally of periods and magnitudes. A pattern of numbers moved the Sun from the center of a chart to a side road in a vast system till, as more clusters were measured, the asymmetry grew clearer. The distribution of globulars sketched the Milky Way's overall size and the direction of its core. But even with the method set, limits pressed in from several directions. Calibration errors could creep in from faulty 0 points. Early parallax values for Cepheids had large uncertainties. The slope of the period-luminosity relation could vary with metallicity, the star's chemical makeup. Cepheids are not all the same. There are at least two populations, Type 1, also called classical Cepheids, and Type 2, older, less massive stars. Both pulsate, but at the same period they have different intrinsic brightnesses. Confusing the two would skew distances. A Type 2 mistaken for a Type 1 would produce a value that was too small, because you would think the star was brighter than it truly is. Observers needed to sort populations using color, spectra, and locations within galaxies to avoid those traps. Dust in our galaxy and in others dims and reddens starlight. If you ignore extinction, you misjudge the apparent brightness and, therefore, the distance early workers applied average corrections, but dust is patchy. Infrared observations help because longer wavelengths slip through dust more easily, reducing the correction. Later, space telescopes would remove atmospheric noise and push measurements into cleaner bands. In Leavitt's era, these were future fixes. The method was sound. The execution would sharpen over decades as instruments improved and samples grew. Another challenge came from selecting the right Cepheids in crowded fields. In a dense star cluster or the core of a galaxy, light from neighbors blends into the target that makes the target seem brighter and flattens its light curve, biasing the periods and amplitude. Careful image subtraction and better resolution mitigate this, but early plates had coarse sampling compared to modern detectors. Even so, the periodic signal is strong. A well-sampled curve shows a rise that is quicker than the fall, a shape characteristic of Cepheids. With enough patience, the pattern stands out from the noise. Despite these hurdles, the relation's power kept drawing astronomers back. A single star's timed flicker offered a way to judge the scale of entire systems. If you could find such a star in a spiral that looked like a galaxy, you could answer whether that spiral resided within the Milky Way or far beyond it. The stalemate from earlier arguments could not survive a direct measurement. One good Cepheid, properly classified and calibrated, would weigh an island of stars. The outcome would not arrive from rhetoric, but from a plotted curve and a distance modulus. The community also learned to chain methods. Cepheids set distances to nearby galaxies. Those galaxies hosted supernovae of a standard type. The supernovae then served as beacons visible far deeper into space, where Cepheids were too faint to detect. Each rung borrowed its scale from the one below it. This is the distance ladder in action, built on Leavitt's relation as a foundation. When the ladder holds, you can trace the size of structures across millions and then billions of light years. Without that first sturdy step, later tools would dangle without support. Shapley's use of Cepheids in globular clusters did more than move the sun. It provided a check on the Milky Way's overall dimensions and suggested a large system with a sun off-center. Those results influenced how astronomers interpreted faint novae in spiral nebulae and the apparent sizes of those nebulae. If the Milky Way was vast, then distant spirals might fit within it. If the Milky Way was smaller, the spirals might be separate. It became clear that the argument could spin until a decisive distance landed. The quiet power of a period luminosity plot could provide that clarity if applied to the right target in a spiral with a clean line of sight. There was also a growing awareness that not all Cepheids behave identically in every environment. Metallicity affects opacity in a star's outer layers, which sets the details of the pulsation. The relation slope and 0 point can shift slightly with composition. Observers began to split samples by galaxy type or use color indices to correct for these effects. More precise photometry and better spectral classification made those corrections practical. Over time, the scatter around the relation narrowed. Distances improved from tens of percent errors down to a few percent in favorable cases. Each refinement turned a broad brush into a finer pencil. By the time large reflecting telescopes and more sensitive plates came online, the method had matured enough to aim beyond our galaxy. A spiral with well-defined stars in its outskirts offered the best chance. The outskirts reduced crowding and dust, and the brightest Cepheids there would stand above the background. Astronomers started long campaigns, returning to the same field night after night, to catch the rise and fall and to build a precise period. The patience paid off when a marked variable star in a known spiral matched the signature of a Cepheid. The period set the absolute brightness. The apparent brightness set the distance. The arithmetic pointed to a location well outside any reasonable boundary for the Milky Way. The elegance of the approach remained the same from the start: period to power, power to distance. Leavitt's original insight did not need flourish, it needed careful observation and calibration. As the data improved, the conclusion hardened. With a handful of well-measured Cepheids, astronomers could lay down a scale for the local universe. Those measurements did not offer opinions. They offered numbers, and numbers, cross-checked with other methods, tightened the frame of our map. So the tool stood ready. A relation born from diligent cataloging, tested across clusters and fields, sharpened by calibration and mindful of its limits. It could carry the weight of a galaxy's distance if used with care. All it required was a clear target. a spiral bright enough to host a Cepheid that our largest telescopes could resolve, and steady time at the eyepiece to catch the rhythm. With that, the long argument over scale could give way to a measured span. A mountain, a mirror, and Andromeda come into focus. Why did one blinking star make the Milky Way feel small? Because a steady beat leaves no room for opinion. When a light repeats with a measurable rhythm, you can turn that pattern into distance, and distance into scale. On a cold mountaintop with a 100-inch Hooker telescope, Edwin Hubble set out to do exactly that. He aimed not at a nearby star cluster or a familiar nebula, but at the large spiral smear in the constellation Andromeda. For years, people argued about what it was. He went to gather more than a nice image. He went to collect time. Night after night in 1923 and 1924, Hubble and the Mount Wilson team exposed glass plates to the same patch of Andromeda. The telescope gathered thin light from a wide field of stars, recording it as tiny black specks. On their own, those specks said little. But when you stack nights, you can ask a different question. Did any of those points change? The technique was patient work. You take a plate from October and compare it to one from November. You mark any star that looks brighter or dimmer, then you check again a week later. Repeat. If the changes line up into a cycle, bright, dim, bright, you measure how long the cycle lasts. That period gives you the key to the star's true output. The tension was simple and unforgiving. If one of those changing stars inside Andromeda was a Cepheid variable, then its period told you how luminous it truly was. Compare that true luminosity to how faint it appears, and the distance falls out of the math. If that distance stretched far beyond any credible size for the Milky Way, the object could not live inside our galaxy. If there was no Cepheid, the argument could continue. The universe could stay cozy and bounded for one more round. On one plate, Hubble scrawled a short note next to a faint speck that had altered its brightness between exposures. They are. That single mark flagged a star whose light rose and fell with a consistent rhythm. He did not stop at one cycle. He kept taking plates and measuring. The brightness curve settled into a clean period. With that number, he could apply the established relation between period and intrinsic brightness. The star's real wattage was not a guess. It was set by the cadence of its pulse. The next step was to compare that intrinsic brightness to the dim glow seen on the plate. The gap between the two values is what distance is made of. The first calculation put Andromeda at roughly 900,000 light-years away. That alone reached beyond most estimates for the Milky Way. Even allowing for wide margins, that figure pulled Andromeda outside the boundaries people had argued for. When later refinements pushed the value upward to about 2.5 million light-years, the conclusion gained even more weight. The exact number changed as calibrations improved, but the direction never reversed. Each correction moved the target farther, not closer. The spiral was not a cloud inside the Milky Way. It was a separate system. What made this so decisive was the method. Hubble did not rely on a single snapshot or on the brightness of an explosion. He used repeated observations over many nights and months, then matched them to a rule that connects time to luminosity. The rule runs both ways: longer period, brighter true output; shorter period, dimmer. Period is something you can time with a clock and a stack of plates that keeps the inference clean. You're not guessing at how much dust blocks the view or how unusual an outburst might be. You measure a rhythm. Even so, the work had to run through error. Photographic plates respond to light in ways that can bias measurements. The weather shifts the contrast. The emulsion grain can hide a small change. To deal with this, the plates were taken with consistent methods, and the measurements were repeated until the curve of the star's brightness settled. The cycle smoothed out the noise. The result was not one value from one night, but a period distilled from many looks at the same star. The magnitude of the distance hit hard because it confronted the size of the Milky Way at the time. If your galaxy spans, say, a few 100,000 light-years at most, and a star in Andromeda tells you the host system sits near 1,000,000 light-years away or more, you cannot tuck it inside. The geometry refuses to bend, and with Andromeda out, other spirals of similar structure likely stand out as well. One measured lighthouse does not light only its own harbor. It tells you that all the harbors you see of that kind are probably farther than your shoreline. The var scribble became a hinge in the story. It is ordinary handwriting next to a very faint blot on a glass plate, yet that note marked a shift from debate to measurement. The excitement did not come as a bang. It arrived as a period in days and a distance in light years. The emotional beat was small and exact, a trace on a curve, a calculation that did not collapse under scrutiny, and a number that made the Milky Way feel provincial. As other plates came in and other stars were timed, the early distance rose. This was not backpedaling. It was the normal arc of a calibration. The relation between period and luminosity depends on the type of Cepheid and the 0 point used in the math. Improvements in those values nudge distances. In this case, they nudge them outward. That trend reinforced the case that Andromeda stands beyond the reach of any map that kept all spirals inside the Milky Way. The correction did not weaken the conclusion. It tightened it. What followed from that conclusion was immediate. If Andromeda is a galaxy, then the Milky Way is not alone. The sky's other spirals are, most likely, peers rather than gas clouds. The universe does not end at the edge of our disk. It stretches into a field of separate star systems, each with their own shapes, clusters, and histories. The island universe idea moved from a bold claim to a measured fact. And a measured fact carries the weight to rearrange a worldview without theatrics. It asks only that you accept a distance. The method Hubble used remained straightforward in principle. Take a deep exposure of a galaxy. Come back regularly and take more. Search for stars that change brightness in a controlled way. Plot their cycles. Measure their periods and apply the relation. This turns a distant, unresolved whirl into a set of individual clocks you can read. If a galaxy holds enough of these clocks and your telescope can separate them from the background, you have a path from appearance to scale. The difficulty was never in the basic logic. It was always in the details. Sensitivity to find the stars at all, consistency to measure small shifts against the plate's grain, and the discipline to keep the schedule and the logbooks on a mountain in thin air. You need clear nights, a stable instrument, and the will to test whether the same faint speck rises and falls on the same timescale again and again. The reward for that patience is a number that does not care about anyone's preferred model. When people talk about this discovery, they often focus on its grand sweep. But the power landed because it was narrow. One object, one kind of star, one set of repeatable steps. The broader implications follow from that single case. You do not have to settle an argument with a grand theory if you can anchor it to a concrete measurement that others can repeat. That is why the VAR note matters. It pointed at a procedure that could be run on other galaxies, and it worked. As telescopes improved, the list of galaxies with measured Cepheids grew. The numbers formed a ladder reaching to ever greater distances. Other rungs, like certain kinds of bright stellar explosions, could then be calibrated against those nearer Cepheids. This let observers carry the scale beyond the reach of even the largest mirrors of that era. Hubble's first steps on Andromeda thus fed a larger effort to build a consistent map of space that did not depend on local assumptions about our own galaxy's size. The change in mindset settled slowly, but it held. Once the distance to Andromeda cleared the Milky Way's plausible edge, the debate about whether all spirals are inside our galaxy lost its footing. New surveys catalogued galaxies as separate systems. Sky maps filled with objects that were not part of the Milky Way structure. The term nebula shifted in usage, and the language of astronomy adjusted to the new scale. What had been a question became a foundation. The reason that one blinking star made the Milky Way feel small is that it set a scale you could not ignore. A rhythm became a ruler. The ruler stretched across a gulf that no adjustment to the Milky Way's size could swallow, and because it relied on timing, it left little room for subjective interpretation. The data told a clean story, a cycle of light, a computed luminosity, a measured distance, and a conclusion about where the spiral must live. So the payoff is direct. Andromeda stands apart as a galaxy in its own right. The universe, once thought to be a single system, now holds the Milky Way as one member of a much larger set. Not an exception, not a container, just another island among others. With that gate open, the next steps turned from whether there are other galaxies to how to measure the one we live in and how to place it within the larger structure. The shift moved from counting spirals to finding our coordinates, our center, our arms, and the shape of the space that holds them. How do you map a house you can't step outside of? You start by learning which windows still give you a view. Starlight in visible wavelength runs into dust grains that float through the Milky Way's disk, scattering and absorbing it, so the view looks patchy and dim. That is why early sketches of our galaxy leaned on what could be seen between the clouds and ended up distorted. To fix that, astronomers turn to light that dust lets pass and to stars that carry built-in distance clues. The goal was simple and hard at the same time. Find the center, trace the arms, and measure how far the disk runs before it thins into the halo. Radio waves at 21 centimeters became the workhorse. Neutral hydrogen atoms flip the spin of their electrons and protons and release a photon at that specific wavelength. Dust barely touches that signal, so radio dishes can sweep the plane of the galaxy and record the hydrogen's faint glow all the way around. The hydrogen spectral line shifts in frequency because of motion, and that shift translates into velocity along our line of sight. By combining these velocities with a model of how the galaxy rotates, you can lay down a map of spiral features and gas lanes, even on the far side of the center. Infrared observatories add another layer. They watch the heat from cooler stars and warm dust, which slips through the murk, revealing the dense swell of the central bulge and the bar that cuts across it. The bar matters because it channels gas toward the core and sets the pattern speed of the inner galaxy, which in turn shapes how arms unfurl. Stars with known behaviors act as signposts. RR Lyrae variables, common in older populations, have stable brightness patterns that make them reliable distance indicators for the thick disk and halo. Younger Cepheid variables, brighter and fewer, trace fresher star-forming regions along the arms. With these two sets, you can plot old streams and young arcs and see how the Milky Way layers age and structure. The European Space Agency's Gaia mission pushes this further by measuring tiny shifts in star positions over time. Those parallax motions give direct distances for vast numbers of stars, and proper motions show how they drift through space. Together, they provide a three-dimensional view of our local spiral segment and the motion of clusters and associations that ride the arm we live on. For pinpoint geometry in dense or obscured regions, astronomers use mesas, natural microwave lasers from molecules like water or methanol in star-forming clouds. Very long baseline interferometry links radio antennas across continents and resolves these masses with microarc. Second, precision. Tracking them over years gives both their angular drift and their Doppler speeds. That dual information delivers geometric distances to regions on the other side of the galaxy and nails down the rotation curve, which is the plot of orbital speed versus distance from the center. The rotation curve's shape is a key clue to the mass that holds the disk together. Even with those tools, early maps struggled because assumptions about symmetry and rotation could bias the result. Dust lanes hide entire stretches of the inner disk in optical light, pulling early estimates of the arm layout toward what could be seen rather than what was there. Infrared and radio corrected that, showing that the Milky Way is not a simple grand design two-arm system, but a barred spiral with multiple major arms and spurs. The bar in the core stands out in infrared counts of old stars. It spans the bulge and tilts relative to our line of sight, so the near end appears brighter in one direction of the sky, and the far end fainter in the opposite direction. That tilt helps explain asymmetries in star counts from Earth and fixes the angle of the bar with respect to our position. In the center lies the compact radio source known as Sagittarius A star. Stars very close to it whip around on tight, fast orbits that take years, not millennia. By following their paths and speeds, researchers derive the mass required to hold them in place. The numbers add up to about 4 million times the mass of the Sun, confined to a region smaller than our solar system, which points to a supermassive black hole anchoring the core. That central engine shapes the immediate environment, heating gas, stirring magnetic fields, and occasionally flickering as material spirals down. It does not dominate the mass of the galaxy, but its presence marks the dynamical heart. Tracing the arms, radio surveys of hydrogen and carbon monoxide highlight cold gas where stars form. Those lanes wrap around the bar and extend into arcs that we label as the Perseus, Scutum Centaurus, and Sagittarius Carina arms, among others, with smaller bridges and offshoots. Young clusters, H2 regions, and massive stars align along these features, confirming their identity as star-forming arms. Meanwhile, older populations fill the thick disk and halo, less tied to the spiral pattern. The overall disk stretches roughly 100,000 to 120,000 light-years across when you count the outer gas layers and faint stellar periphery. The bright stellar disk is smaller than the farthest gas, which can reach farther into the dark halo. The Sun system sits in a minor structure, often called the Orion Spur, a short arm segment between two larger arms. Our spot is about 26,000 light-years from the center and slightly above the midplane of the disk. That offset is modest, but it affects the dust we look through toward different longitudes, which is one reason some windows on the sky feel clearer than others. Being in a spur rather than a crowded main arm means the local density of giant molecular clouds is lower on average than in the core of a major arm. That has implications for star formation near the Sun and may play a role in long-term stability for planetary systems. Counting stars across the disk is not a matter of tallying dots. You model the luminosity function, account for dust and distance, and fold in Gaia's parallax catalog and proper motions to reduce biases. Those estimates land in the hundreds of billions of stars spread across a range of masses and ages. The disk contains the bulk of them, but the central bulge hosts a dense old population, and the stellar halo holds ancient metal-poor remnants along with streams left by dwarf galaxies that the Milky Way has accreted over time. These streams arc high above and below the plane and trace the gravitational field, adding another handle on the mass distribution. The rotation curve tells a story the starlight alone cannot. If only visible matter counted, orbital velocities would drop with distance from the center after peaking close, and measurements show that speeds stay roughly flat out to large radii. That implies more mass than the stars and gas can account for, spread in an extended halo that envelopes the galaxy. This dark matter halo sets the depth of the potential well, slows the drop-off in rotation, and shapes how satellite galaxies move. It also influences how bars and spiral patterns evolve, because it changes the way angular momentum flows through the disk. To set the scale, Distances to the center have been refined using stellar orbits around Sagittarius A star, Masdar parallaxes in the inner arms, and statistical fits to Gaia data that converges on a central distance of about 8 kiloparsecs, which matches the 26,000 light-year figure. The bar's length and angle follow from infrared star counts and kinematics, and the disk's thickness comes from vertical motions in Gaia's catalogue. Ripples in those motions hint at past interactions, possibly with passing dwarf galaxies that have stirred the disk and left waves propagating through it. These subtle patterns, mapped in velocity space, act like seismology for the galaxy, revealing internal structure and recent history. Dust itself becomes a tool when mapped in 3 dimensions. By comparing the colors and brightness of stars at known distances, researchers build volumetric dust atlases that show where the clouds thicken and where tunnels of lower extinction open. Those maps guide where to look for star-forming regions and help correct photometric surveys so that counts and colors reflect intrinsic properties rather than reddening. Infrared surveys trace the glow of the dust grains, revealing the skeleton of the interstellar medium. Combined with radio maps of gas, they show how matter cycles between cold, dense clouds and diffuse phases, fueling new stars, then getting enriched and pushed around by stellar winds and supernovae. Maser spots in high-mass star-forming regions add anchors across the disk. Each region offers a geometric distance and a full 3-dimensional velocity vector, with dozens spread around the galaxy. The rotation model becomes less dependent on assumptions. The pattern speed of the bar and the corrotation radius of the spiral arms can be constrained, which helps determine how gas flows through the inner galaxy, where shocks form and where star formation concentrates. These flows feed the central molecular zone, a dense ring of gas within a few hundred parsecs of the core, where conditions differ from those in the disk. As the map sharpened, the Milky Way emerged as a barred spiral with several major arms, a dense bulge, and a central black hole. Its disk spans on the order of 100,000 light-years, hosting hundreds of billions of stars. It rides in a dark matter halo that extends far beyond the visible edge and governs the outer rotation. Our address sits a comfortable distance from the center, in a spur that branches between 2 dominant arms. The numbers are not decorations, they are working coordinates that let us test models of how galaxies organize gas, form stars, and evolve over billions of years. Knowing this layout changes how we read the sky. When we look toward Sagittarius, we peer through the crowded inner disk and into the bulge, where dust blocks much of the starlight but radio and infrared penetrate. When we sweep toward the anti-center, we trace the outer arms where young clusters and H2 regions mark recent star formation. Above and below the plane, we pick up halo stars and streams that whisper of past mergers and ongoing accretion. Each direction ties into a piece of the structure that the tools have laid out, and each measurement helps refine the underlying mass model. The result is a home we can describe with scale, coordinates, and motion. A barred spiral about 100 to 120,000 light-years across, with a 4 million solar mass black hole at its center, hundreds of billions of stars spread through disk and bulge, and a dark halo that shapes its spin. Our solar system orbits at roughly 26,000 light-years from the core, in the Orion Spur, circling the galaxy on a path that takes a couple of 100 million years to complete. The map is not perfect, but it is coherent. It tells us where we are and what surrounds us, even though we cannot step outside for a snapshot. Now, step beyond the house and look down the street. Farther means earlier because light has a speed limit. A photon leaving a distant galaxy needs time to cross the expanding space between us. By the time it reaches our detectors, we are seeing that galaxy as it was, not as it is now. That's the core trick that turns a telescope into a time machine. It also creates a practical challenge. The further back we reach, the fainter the signal becomes. galaxies from early epochs are small, low in heavy elements and forming stars rapidly. They throw out light, but cosmic expansion stretches that light into redder wavelengths on its way to us. So two hurdles stack up: dimmer targets and redder light, making sensitivity and wavelength coverage the decisive factors. Astronomers learn to lean into patience. The Hubble Space Telescope stared at a tiny, unremarkable patch of sky for many hours and then many days. Stacking exposures, that effort produced the Hubble Deep Field, and later, the Ultra Deep Field. The trick was simple in concept: gather more photons by integrating longer. The results were not spectacular in fireworks, but in number. Thousands of faint smudges appeared in what looked like empty sky, each a galaxy at a different stage of its life. The implication was straightforward and huge. If a pinhead patch of the sky holds that many galaxies, the full sky holds an extraordinary number. The deep fields transformed suspicion into evidence. The universe is saturated with galaxies and the past is crowded. The cost of seeing so far back is redshift. As space expands, it stretches the wavelength of light in transit. The original ultraviolet and visible light from early stars and gas arrives at Earth, shifted into the infrared. That's where the James Webb Space Telescope picks up the baton. Its mirrors and instruments are tuned for infrared light, and its location and cooling let it work in low background heat. This opens a band of the spectrum where early galaxies glow brightest after their journeys through an expanding universe. Webb doesn't just see farther in distance, it sees earlier in time because it catches the wavelengths where the oldest signals now lie. Ground-based telescopes had to solve a different problem. Earth's atmosphere blurs. Adaptive optics tackles this by measuring distortions in the incoming wavefront and reshaping a mirror in real time to cancel them out. It's not conceptually unlike noise-canceling headphones, only it works with distorted starlight and flexible optics. With adaptive optics, large observatories can resolve details that used to be lost, complementing space telescopes with sheer collecting area. That sharpness helps when measuring shapes, sizes, and internal motions of distant galaxies, especially when paired with long exposures and careful calibration. Deep field observations work because the universe, on large scales, is statistically uniform. Stare at one blank patch and you sample the general census. The thousands of galaxies in those images cover a ladder of redshifts, which is another way of saying a ladder of times. Their colors trace star formation and dust. Their shapes hint at mergers and growth. Their brightnesses, once corrected, hint at masses and ages. Each added exposure reduces noise and brings another faint galaxy across the detection threshold, turning a dark region into a layered archive. Redshift is more than a color shift. It encodes expansion history. The relation between redshift and distance is not linear over cosmic time because the expansion rate has changed. That's why spectra are vital. By spreading a galaxy's light into a rainbow, observers identify known absorption and emission features at shifted wavelengths. Those shifts give a redshift number, which situates that galaxy on the timeline. Broadband imaging gets you candidates. Spectroscopy yields the timestamps. When Webb started collecting deep infrared data, early catalogs flagged objects with very high redshifts, meaning their light left when the universe was only a few 100 million years old. These candidates appeared surprisingly bright and massive based on initial assumptions. That prompted fresh work on calibration, contamination by lower redshift interlopers, and more careful spectroscopy. The picture that emerged still pushes galaxy formation timelines. Stars and structure formed quickly. Whether that means star formation was more efficient, dust appeared earlier, or our models need tuning, the observations sharpen the questions. The faintness problem doesn't just test detectors, it tests strategy. Long integrations tie up telescope time. Observatories balance deep looks at small areas against shallower surveys of large fields. The two approaches feed each other. Wide surveys find rare, bright objects and map large-scale structure. Deep fields dig into the low luminosity end, capturing the bulk of the population. Together, they give a more complete inventory and help estimate how many galaxies exist at each epoch and brightness. Cosmic dimming also grows with distance in another way. Surface brightness falls off dramatically due to expansion, not just inverse square distance that makes the smearing effect of the atmosphere more damaging for faint, extended objects, and it makes space-based platforms powerful despite smaller mirrors. With infrared instruments, Webb reaches the wavelengths where early hydrogen and dust re-emit absorbed energy, revealing star-forming regions and the glow of warmed dust. That glow can hide or reveal star birth depending on how much dust is present and how it is distributed. Every deep field is a mosaic of histories. The most distant galaxies appear compact, clumpy, and irregular. Closer ones show settled disks, bars, and spirals. That morphological trend, while not perfect, supports the view that mergers and gas accretion build structure over time. The timeline is not a single narrative, though environments vary. Dense regions trigger early collapse and rapid assembly. Voids delay structure growth. Telescopes, by sampling many lines of sight, begin to average over these differences and reveal the common threads. Ground-based giants add spectroscopy at scale. Multi-object spectrographs put slits on hundreds of targets in one shot, mapping redshifts across fields. Adaptive optics, combined with integral field units, lets astronomers measure velocity fields within galaxies, tracing rotation, turbulence, and outflows. Those measurements show how gas settles into disks, how feedback from young stars stirs the medium, and how central regions grow. When paired with deep imaging, kinematics turn still frames into clues about the hidden motions that sculpt shapes. Infrared time travel also intersects with the cosmic microwave background indirectly. The earliest galaxies help reionize the universe, turning neutral hydrogen into a plasma that lets ultraviolet light travel farther. The timing and progress of reionization leaves signatures in what wavelengths escape unimpeded. Deep infrared observations pick up the Lyman break sliding through filters as redshift increases. Identifying that break efficiently sifts high redshift candidates, later confirmed by spectra, with lines shifted far into the infrared. Noise is a constant companion in this work. Detector noise, zodiacal light from dust in our solar system, air glow for ground-based sites, and even cosmic rays hitting detectors add contamination. Long exposures and careful processing separate signal from these backgrounds. Dithering, shifting the pointing slightly between exposures, helps fill gaps and average out detector quirks. Calibration with standard stars ties fluxes and colors to consistent scales. None of these steps is glamorous, but they make the scientific payoffs reliable. The payoff is not distance for its own sake. It is history. Galaxies in deep fields let us reconstruct star formation across time. Rates rise from early epochs, peak a few billion years after the Big Bang, and then decline. Metals, elements heavier than helium, build up as stars live and die. Dust grows from those metals. Structure emerges from clumps. The universe transitions from opaque to transparent to richly structured. Telescopes, by targeting different wavelengths and depths, stitch these transitions into a continuous narrative. Redder wavelengths are a necessity, not a convenience at high redshift. Emission lines from hydrogen shift out of the visible bands. Infrared coverage brings those lines back into reach. Instruments with high sensitivity at these wavelengths turn almost invisible smudges into measurable objects. Once redshifts are secure, sizes in angular units convert to physical sizes with the right cosmological model, giving scales that show how compact early galaxies were compared to later ones. Even those compact sizes carry clues: high star formation per unit area, intense radiation fields, and strong winds. Some of the most informative data come from stacking. When individual galaxies are too faint to measure certain features, astronomers align and average many of them to enhance the signal. Stacking can reveal typical spectra, dust content, or X-ray emission from populations collectively, even when individuals fall below detection. This statistical approach lets deep fields do double duty, resolve what's bright enough, and infer the rest from aggregates. The lesson from all these methods is steady. Looking farther shows earlier phases. Each instrument and technique brings one part of the spectrum and one slice of time into focus. By combining data, scientists trace how tiny fluctuations turned into stars, then galaxies, then networks. The result reads like a long exposure of becoming, not a static map. You watch the universe grow into itself, one wavelength at a time, and as those snapshots line up from faintest to brightest and from reddest to bluer, a pattern emerges. Galaxies do not evolve in isolation. Their histories bump into each other, exchange gas, and tangle orbits. The timeline our telescopes assemble is a crowded one, and it points to the next step. But galaxies don't live alone. They gather, collide, and weave. What happens when galaxies start keeping company? They stop behaving like isolated pinwheels and start acting like members of a slow, long negotiation. Our own neighborhood shows how this works. The local group holds the Milky Way Andromeda, also called M31, the Triangulum Galaxy, M33, and a few dozen dwarf companions. Each system sits inside a dark matter halo, and those halos overlap and tug at one another. The result is a gravitational conversation that never ends, with paths curving, satellites shifting allegiance, and gas and stars responding to tides that stretch across millions of light years. Even without stepping beyond this small patch of space, you can see the rules that scale up to the largest structures we've mapped. The pull within the local group sets the stage for our future. Andromeda approaches at a few hundred kilometers per second, a motion we detect through its blue-shifted light, and proper motion measurements project the tracks forward several billion years, and the two spirals meet. They won't crash like solid disks. Vast spaces between stars mean direct stellar collisions will be rare. Gravity is the main actor. Tidal forces will twist arms into long streams. Gas will compress in some regions and empty out in others. After a series of passes, the cores will sink toward each other. Dynamical friction will drain orbital energy into the halos in the outer stellar envelopes, and the pair will settle into a single, larger system. Simulations that follow millions of particles show the end product looks like a big, redder, more spheroidal galaxy, what we often call an elliptical remnant. That fate isn't unique. Smaller members of the local group already wear the marks of this process. Dwarf galaxies show tidal tails, shells, and distorted shapes. The large and small Magellanic Clouds trail a ribbon of hydrogen gas, the Magellanic Stream, curving behind them, stripped by tides and by the Milky Way's extended halo. Stellar streams loop through our own halo, the shredded remains of captured dwarfs and globular clusters. These threads are not static. They precess, they thicken, and they reveal clumps in the dark matter distribution. Subhalos that betray the granularity of the invisible mass that dominates the group's gravity. Step outward to the Virgo cluster and the numbers grow fast. Thousands of galaxies share a common gravitational well that spans millions of light years. The space between them is not empty. Hot intracluster gas fills the volume, heated to tens of millions of degrees, glowing in X-rays. You can think of each galaxy as a ship moving through a thin, hot sea. As they move, ram pressure strips their gas. Tails form, star formation shuts down, and spirals fade into smoother, quenched systems. When galaxies pass close to one another, tides pull stars into bridges and plumes over time. Repeated interactions erase disks and leave rounder, redder shapes. The cluster core often hosts a central giant with an extended halo of orphaned stars. Light from galaxies that have been stirred and spread out by many orbits in a crowded arena. We know clusters like Virgo contain far more mass than their stars, and gas can account for. The evidence comes from motions and from how clusters bend light. Galaxy velocities within the cluster rise too high to be bound by visible matter alone. The gravitational potential must be deeper. Gravitational lensing makes this visible. Distant galaxies stretched into arcs near a cluster reveal how much mass sits along the line of sight. Map the lensing pattern, and you get a mass distribution that peaks around the cluster halos, even where the luminous matter is sparse. The arcs don't care about what glows. They respond to gravity from everything, including the dominant dark matter. Mass that you cannot see shapes tidal features too. In simulations, you can dial the amount of dark matter and watch how structures change. With a heavy, extended halo, mergers happen more quickly and streams last longer as coherent features. Without it, the timing, shapes, and survivability of these structures don't match what we observe. The consistency across independent clues, velocities, lensing, and the frequency of quenched galaxies points to a common theme. Dark matter sets the depth of the wells, directs the flow of gas, and choreographs the long-term evolution of galaxies once they join a group or a cluster. Back in the local group, the path toward the Andromeda encounter is already written in relaxed orbits and slow infalls. Our own disk shows signs of past nudges, a warp, ripples in stellar velocities, and asymmetries in the outer gas. Some of these features likely came from the repeated passages of the Magellanic Clouds or other dwarfs. Residual star formation in parts of the disk may tie back to gas funneled in by tides. The interplay of small companions and the main halo seeds, subtle structure that Gaia's precise star maps now trace in detail, revealing moving groups and phase space spirals that carry the memory of earlier interactions. The story scales not only in size, but in time. Groups often merge into clusters, and clusters grow by accreting groups along preferred directions. This happens because matter does not fall in from all angles equally. The underlying dark matter forms filaments, and galaxies flow along these threads like traffic on long, invisible highways. When they reach cluster intersections, nodes, the density is high, the encounter rate rises, and the assembly speeds up. Even within a single cluster, substructure remains. Smaller clumps, the remnants of groups that have only partly dissolved. Their galaxies share velocities and histories, a fossil record of how the cluster built up. You can see the cumulative effects in the intra-cluster light. Between galaxies, a diffuse glow fills the cluster, made of stars flung out during encounters. It is faint, but it is everywhere in dense environments, and it has a distinct spatial distribution. It traces the orbits of satellites and piles up where tidal forces are strongest. It is a direct measure of how much merging and stripping has occurred, and it grows with time as clusters mature. The process that brings us together with Andromeda echoes this broader behavior. The local group orbits within a larger basin of attraction. Nearby groups move in correlated ways, streaming toward regions where the density of matter is higher. Over tens to hundreds of millions of years, these motions add up to a flow pattern that connects smaller structures to larger ones. The Virgo cluster exerts a pull, and beyond that, even larger associations guide the currents of galaxies. The velocities we measure are not random. They align with the shape of the density field around us. Gravitational lensing offers a clear visual cue for these dynamics beyond velocity data. In massive clusters, background galaxies stretch into thin blue arcs that wrap around the mass peaks. Sometimes, multiple images of the same galaxy appear. Strong lensing highlights the densest cores, while weak lensing, statistical distortions of many faint galaxies, maps the mass over wider regions. Together, they show a skeleton of gravity-filled structures that the luminous matter only partly outlines. This technique does not rely on the details of the galaxies themselves. It reads the curvature of space created by mass, making it a direct test of the potential well in which the cluster resides. For groups, lensing is subtler, but it still works when stacked across many systems. The signal confirms that even small associations, like the local group scale, sit inside extended dark matter halos. That halo shapes the paths of satellites, the truncation of their gas reservoirs, and the timing of when they stop forming stars. When a dwarf falls in, a combination of tidal forces and the pressure of hot gas shrinks it and strips it. Whether it survives as a compact, dead remnant or dissolves into a stream depends on the orbit, the mass ratio, and the density of the surrounding medium. As we scale up to superclusters, we start to talk about how whole clusters move relative to one another. Their motions form part of a larger pattern, flows that converge towards central regions. These are not bound in the way individual clusters are, but the pattern of overdensities still shapes the roots. The name we use for our greater neighborhood reflects this idea, a vast region that contains many clusters and groups, all tracing a common landscape of gravity. At its center lies a zone whose pull organizes the paths of the surrounding galaxies and clusters, a sign that even at these grand scales, gravity still lays down preferences for where matter will travel. When you link local group dynamics to cluster assembly, a simple picture forms. Galaxies collect into small associations. Small associations feed clusters, and clusters sit within larger currents. The same physical ingredients govern each level. Gravity from dark matter halos, gas dynamics in hot media, and the slow exchange of energy and momentum through tides and friction-like processes in collisionless systems. Each merger redraws the map. Each stripping event leaves a tracer of where and how the last encounter unfolded. So our galaxy is not drifting alone. It belongs to a moving, merging community shaped by scaffolding we cannot see directly. We read the scaffold in orbits, in faint streams around our halo, in the arcs that ring distant clusters, and in the diffuse glow that fills the space between their members. The present layout is a snapshot in a long sequence. Billions of years from now, the local group will look simpler. A single, larger galaxy surrounded by the remnants of dwarfs. And the broader region will have reorganized as groups funnel more mass into the nearest attracting zones. All of this local motion adds up to a larger pattern. Local flows feed into basins that define supercluster scale structure. Follow those flows and you start to see how the map guides the traffic. The rivers of galaxies have sources and mouths, and their channels cross and merge. Keep tracing them and the view widens from a neighborhood to a continent. Now it's time to set the local currents aside and step onto that continent to see how those channels knot together into the greater watershed of the cosmic web. Why do galaxies line up like dew on threads? The sky does not scatter them at random. When astronomers charted positions on wide surveys, a pattern came into view. Long, thin chains of galaxies stitched across space with broad, empty gaps in between. That layout is not cosmetic. It reflects how matter settled over billions of years, guided by gravity acting on small seeds laid down early. The map looks like a network because the universe grew with preferences, funneling material along paths where gravity's pull was slightly stronger and leaving behind vast, quiet cavities. The first hints came from redshift surveys that did not stop at counting bright smudges. They measured distances and built three-dimensional catalogs. Slice the data and you find walls, filaments, and nodes where many strands meet. Some structures run for hundreds of millions of light years. Voids of similar scale interrupt them, nearly devoid of luminous galaxies. In these surveys, Clusters sit at the junctions like cities at crossroads. Between them, filaments act as highways feeding matter inward. The pattern is statistical, not perfect. Chance still plays a role. But the overall geometry persists across independent datasets and methods. If stars and gas were the whole story, these features would be hard to grow in the available time. Gravity alone, acting on the visible matter we see, would not collapse structures fast enough or hold clusters together at the observed speeds. The mass budget comes up short. That gap points to a background component that does not shine, interact with light, or collide the way gas does. This component adds mass where telescopes see little and deepens gravitational wells so the scaffolding can form early and persist. The web's shape, thickness, and the timing of its growth all point in the same direction. Cold, dark matter gives the missing backbone. Cold means the particles move slowly compared to the speed of light in the young universe, so they clumped efficiently on small scales. Start with tiny density variations left from the early plasma. Let gravity amplify them. Regions a bit denser pull in more material and become denser still. In simulations that follow this recipe, particles gather along sheets, then filaments, then into halos at intersections. Gas falls into the same wells, cools, and forms stars. The resulting mock maps look like the survey maps. Change the particle speed or remove the dark matter and the pattern no longer matches what we observe. Over time, this process produces superclusters, not bound as single objects, but connected regions with coherent flows. Our home sits inside one such basin called Laniakea, an area defined by the way galaxies stream under gravity toward shared attractors. If you plot the motion of galaxies after subtracting cosmic expansion, arrows converge along threads into denser knots. The structure does not have sharp borders. The boundary is a surface where flows diverge. Within it, the Virgo cluster and other groups occupy nodes on the same network. The concept reframes the neighborhood. Not a list of nearby galaxies, but a map of directions in which they tend to fall. Large surveys reinforce this view with statistics rather than anecdotes. The Sloan Digital Sky Survey mapped redshifts for millions of galaxies and quasars, tracing the honeycomb of filaments and voids over a broad swath of sky. The 2DF Galaxy Redshift Survey, with a different telescope and strategy, found the same correlation patterns and clustering scales. From these catalogs, astronomers extract the power spectrum of galaxy distributions, a measure of how clumpy the universe is at different sizes. That spectrum follows the curve expected if cold dark matter seeds the web and if dark energy influences growth on the larger scales. Cosmic microwave background maps supply the starting conditions. Temperature anisotropies trace density ripples when the universe was young, and their statistical properties set tight limits on the total matter, the fraction in baryons, and the geometry of space. The Planck mission measured these patterns with high precision. Plug those parameters into simulations and evolve forward. The predicted web aligns with what SDSS and 2DF actually see. It also reproduces specific imprints like baryon acoustic oscillations, faint, regular bumps in the clustering signal that act as a standard ruler across cosmic time. Some of the most direct evidence for dark matter and for the web's invisible framework comes from gravitational lensing. Mass bends light. When a massive cluster sits between us and more distant galaxies, their images stretch into arcs and rings. The degree and shape of that distortion reveal where the mass lies, independent of how bright it is. In many clusters, the lensing maps peak at locations that do not coincide with the hot gas that carries most of the normal mass. The gas, visible in X-rays, can be slowed by collisions and lags behind the bulk of the mass, inferred from lensing, sails through, offset from the gas. This decoupling shows that most of the mass does not collide like gas, supporting a dark component with weak interactions. A well-known case presents the logic cleanly. Two clusters have passed through each other. The gas clouds slammed together and piled up, glowing in X-rays. The overall gravitational field, mapped through lensing of background galaxies, sits ahead of that gas, aligned with the galaxies that move through. If gravity came solely from normal matter, the lensing peak would sit where the gas mass sits. It does not. That offset isolates the mass that neither shines nor collides, behaving as a distinct component. It is hard to tune alternative gravity alone to match both the lensing signal and the gas distribution without invoking extra invisible matter. Follow the filaments further, and you find them feeding clusters with a steady drizzle of galaxies and diffuse gas. In some cases, telescopes detect the intra-cluster medium being heated by infalling material along preferred directions, consistent with streams. Weak lensing across wide fields shows low-contrast mass bridges between cluster pairs, not obvious in starlight, but present in the gradients they imprint on background galaxy shapes. These bridges fill in the picture between the bright nodes. At the largest scales, voids are not absolute emptiness, but low-density regions with faint, sparse galaxies and different galaxy types than dense regions. The environment shapes star formation histories, with denser filaments quenching some galaxies faster. The web also provides context for rare extremes. Supermassive black holes and giant galaxies tend to live at nodes where multiple filaments converge. Starburst activity triggers during mergers that occur more often in crowded intersections. Long radio jets from active galactic nuclei align with filaments that channel gas into halos. Over several billion years, the average galaxy's path through the web affects its supply of cold gas, its merger rate, and its chance of becoming a quiet elliptical or remaining a disk that forms stars. Numerical experiments help test this growth. Start with initial conditions drawn from microwave background measurements. Trace billions of particles under gravity and simple physics for cooling and star formation, and then compare the synthetic universe to data. The two match in where filaments appear, how big voids are, and how cluster masses distribute adjust the recipe, and the matches degrade. Warm dark matter, for instance, would smear out small structures too much. Hot dark matter would keep even larger ones from forming in time. The cold variant fits the observed ladder of scales, from galaxies to the web. As we sharpen these maps, the role of dark energy shows up in how quickly structures grow. The expansion stretches space, slowing the collapse of new clusters and freezing the growth of the larger structures. Measurements of clustering at different redshifts, weak lensing shear fields, and counts of massive clusters over time all fold into constraints on the balance between matter and dark energy. Within current uncertainties, a model with a cosmological constant and cold, dark matter reproduces both the early universe and the texture of the present-day web. Though the web is vast, we can trace it only where light has had time to reach us. That means every filament we draw is part of a sphere, limited by the age of the universe and the rate of expansion. Within that sphere, the scaffold looks continuous. Beyond it, we cannot say what lines continue or whether new features wait. This limit is practical, not a statement that the network stops. It marks the portion of the map we have had time to fill in. The payoff is plain. The large-scale structure is real and mostly hidden from direct view. Stars and gas outline it, but the mass that holds it together does not shine. Gravitational lensing weighs it. Galaxy motions respond to it. Simulations seeded by early universe data grow it. Surveys see the same scales repeating across methods and instruments. The picture that emerges is a lattice threaded through space, with bright matter as tracers riding on a deeper, heavier frame. With the scaffold in hand, a new question rises. How far does this pattern extend, and what sets the limits of our map? The next step is to define what we mean by the horizon. and why stopping there does not imply a wall waiting in the dark. So why does a universe that's about 13.8 billion years old span roughly 93 billion light-years across? The short answer is that the distance between points in space can grow while light is on the way. The longer answer needs a few careful definitions because distance in a changing space-time is not a single thing. If we separate what we mean by how far light has traveled, how far something is right now, and how that distance changes as the universe expands, the puzzle starts to untangle without any tricks. Start with light travel distance. That's the literal time the light took to reach us, converted into how far light would have gone in static space. When you hear that a galaxy's light took 10 billion years to get here, that's a light travel time of 10 billion years. If the universe weren't expanding, you could multiply by the speed of light and call that the distance. But space has been stretching the whole time, so the place the photon left and the place it arrives are not connected by a fixed ruler. Now add co-moving distance. This is a way to label positions, so that as the universe expands, the coordinates of galaxies that flow with the expansion don't change. Think of co-moving coordinates as grid lines painted on space that stretch with everything else. The co-moving radius of the observable universe is about 46.5 billion light-years double. That for a diameter, and you get roughly 93 billion light-years. That value does not contradict the 13.8 billion year age because it's not a light travel distance. It's the separation right now. After accounting for all the stretching that happened while the light was en route, there's also proper distance, which is the physical separation between 2 points. At a given cosmic time, if you could freeze the expansion and lay a measuring tape across space at that instant, proper distance today to the farthest light we can see equals the co-moving distance today, because by definition, co-moving coordinates are scaled to the current size of the universe. But proper distance in the past was smaller by the scale factor, which tracks how much the universe has expanded since then. As the scale factor grows, wavelengths grow with it, and distances between unbound objects grow too. This is where intuition stumbles. We're used to motion, meaning an object moves through space. In cosmology, most galaxies aren't speeding through a static arena. Instead, space between them increases. Two galaxies can be receding from each other faster than light without breaking physics because nothing is outrunning a light beam locally. The metric that measures distance is changing. So a photon can spend billions of years crossing expanding space while its destination keeps moving away. And by the time it arrives, the space it traversed has stretched to far more than a simple time speed would suggest. To anchor these abstractions, we use a snapshot from when the universe became transparent, the cosmic microwave background. About 380,000 years after the Big Bang, the plasma of electrons and protons cooled enough to form neutral hydrogen. Free electrons stopped scattering photons so efficiently, and light began to stream freely. That glow still bathes the sky as a near-uniform microwave signal. The surface we see it coming from is like the last scattering fog bank around us. Its redshift tells us how much the universe has expanded since that epoch, and small temperature variations across it record the seeds of structure. From that surface inward, we tie redshifts of galaxies and quasars to a model for expansion to convert what we observe into distances. The redshift is not only a Doppler effect in an expanding universe, it's the stretching of space increasing the wavelength. The relation between redshift and distance depends on parameters like the current expansion rate and the contents of the universe. When we fit observations, we get a consistent co-moving radius of about 46.5 billion light-years for the observable sphere. The diameter then comes to about 93 billion light-years. How do we calibrate the expansion history well enough to trust those numbers? Several independent rulers and clocks help. One is baryon acoustic oscillations, a preferred separation scale imprinted in the distribution of galaxies by pressure waves that traveled through the hot plasma before recombination. That scale acts like a standard ruler. We know its length in co-moving coordinates, so we can see how large it appears at different redshifts and infer how the scale factor grew. Another is Type Ia supernovae, which behave like standardizable candles. Their peak brightness correlates with how their light curves stretch in time. By comparing their intrinsic luminosity to how bright they look, we estimate distances, and by matching those to redshifts, we trace the expansion rate over cosmic time. These methods agree with each other and with the microwave background's pattern of fluctuations. Together, they outline a history in which the early universe expanded rapidly, slowed as matter's gravity tugged on everything, and then, in the more recent past, accelerated due to a component we call dark energy. Integrating this history gives the co-moving distance to our horizon today because space has been expanding all along. The proper diameter now of the region that has sent us light since the beginning ends up far larger than the naive 2 times 13.8 billion light-years. A common sticking point is the word edge. The observable universe has a horizon because light has a finite speed, and the universe has a finite age. There are regions so far away that their light has not had time to reach us since the first light could travel freely. That boundary is not a wall in space. It's a limit in time and causality. If you could wait long enough without the expansion accelerating, more of the universe would become visible as light from beyond our current horizon finally arrived. With accelerated expansion, future horizons complicate that picture, but the key idea remains. Our view is bounded by what light can do in a dynamic space-time. So the 93 billion light-years figure is not a contradiction to the universe's age. It's the natural outcome of combining how light propagates with how the scale of space changes. A photon emitted when the universe was a few 100,000 years old has been en route for 13.8 billion years of cosmic time, but the landmarks between emission and arrival have moved apart. When the photon set out, the co-moving separation to us was smaller. Today, when we ask how far away the region that emitted it is, we must answer in the current scale of the universe, and that's where the larger number comes from. There's another subtle point. Because objects at high redshift were much closer together when they emitted the light we now see, the light travel distance to them can be less than their current proper distance. For instance, a galaxy whose light has been traveling 12 billion years might now be in proper distance, over 20 billion light-years away. Numbers like these vary with the exact cosmological parameters, but the pattern is the same. Travel time undercounts current separation because expansion stretched the baseline while the photon was in flight. What if we try to go beyond the horizon? We can't. Not by looking. The observable universe is a sphere centered on the observer because the speed of light and the age of the universe define a light cone. Someone in a distant galaxy has their own observable sphere overlapping with ours, but centered on them. The true universe can extend well beyond both spheres. The research consensus allows for the possibility that the total universe is much larger than the part we can see, and it could even be infinite. Our measurements do not impose a physical cutoff at the edge of our view. They only describe the part of the cosmos in causal contact with us. It helps to think of the observable region as a bubble in a much larger ocean. The bubble's size grows with time as more light arrives. But because the expansion of space also changes with time, especially with acceleration, some regions recede from us so fast that light emitted now will never reach us. That future horizon is different from our current particle horizon, but both are limits set by the interplay of expansion and the speed of light. In the present discussion, the 93 billion light-years refers to the diameter of the sphere from which light has had time to reach us by now. The measurements we use to establish these scales rely on statistical patterns across huge samples. Galaxy surveys map the large-scale distribution that reveals baryon acoustic oscillations. Catalogues of supernovae at different redshifts lay out the expansion over billions of years. The cosmic microwave background provides a reference at high redshift. When you fit a model that matches all three, the co-moving distances fall into place and the 46.5 billion light-year radius follows. The agreement across tools gives the number its weight. This way of slicing distance may feel abstract, but it ties directly to what telescopes record. When we report a galaxy at some redshift, we can tell you its look-back time, which is like the light travel time, its luminosity distance, which links to how bright it appears, and its co-moving distance, which fixes its place on the growing grid of the universe. Each answer is a valid distance for a specific question. Confusion sets in when we swap them without noticing. Keep the definition straight and the numbers line up. All of this brings us back to the core point. The observable universe is a limited domain, not the full extent of reality. Our bubble reflects how far light has reached us since transparency, scaled by how space has grown in the interim. That's why we get a diameter near 93 billion light-years without any paradox. If we accept that our vision is horizon-bound, the next question becomes more interesting than the numbers themselves. If our bubble has a horizon, what sits beyond it, and how will that horizon shift as the universe continues to evolve? What does it mean for a galaxy to drift so far that its light can no longer arrive, no matter how long we wait? It means the stage is moving beneath the actors faster than their voices can carry in a universe where expansion accelerates. Farther can become forever, even for things that once shared our sky. Today's distant companions are tomorrow's missing neighbors, not because they end, but because the space between us grows beyond the reach of signal and return. Dark energy drives this acceleration. It behaves like a near-constant energy density in space, so as space expands, the total dark energy increases and pushes expansion faster. In such a cosmos, there exists a future event horizon, a limit set not by walls, but by time. Anything now beyond a certain moving distance will never send a photon that can catch us, regardless of patience or technology. The horizon isn't a ring we could visit. It's a consequence of the expansion history encoded in the universe's geometry and energy content. We can calculate it, track how it shrinks or grows in co-moving terms, and connect it to the fate of information itself. This creates an odd tension with our tools. Telescopes improve, detectors become more sensitive. We build larger mirrors and broader arrays. Yet even with better instruments, some galaxies we see today will fade below any possible detection. Their light stretches to longer wavelengths as space expands, losing energy, thinning out across expanding volume. Past a point, the photons become so redshifted and sparse that no receiver can recover a signal from the noise. That loss is not a technological failure, it is a physical ceiling imposed by the fabric of the universe. The practical outcome is stark. Over the next tens of billions of years, galaxies outside our local gravitationally bound region will drift beyond the event horizon. Their signatures will redden into radio, then into wavelengths so stretched that the signal drowns in cosmic backgrounds and instrument limits. They do not cease to exist. They cease to be reachable. For observers far in the future, the sky will simplify. The distant web will dissolve into darkness. What remains nearby becomes the entire knowable landscape. Our local group stands out as an exception. Gravity here is strong enough to counter the expansion on these scales. The Milky Way and Andromeda will merge in a few billion years, and the debris of that collision, plus our satellite galaxies, will likely settle into a massive bound system. Dark energy doesn't pull apart what gravity has already tied together. The local structure remains intact, while the broader universe recedes. This bound island becomes the laboratory, the archive, and the horizon, all at once for any civilization that inherits it. When we pull back to consider overall shape, observations point to a flat geometry on large scales. Measurements of the cosmic microwave background, galaxy clustering, and the Hubble parameter converge on spatial flatness within tight limits. A flat universe can be infinite in extent, but flatness alone doesn't guarantee infinity. Topology matters. Space can be flat and still fold back on itself in a way that creates a finite volume. In that case, traveling in a straight line long enough could, in principle, bring you back to your starting point without any curvature, the way a video game map wraps around. One possibility is a three-dimensional torus. Think of space with identifications along three directions, so faces match seamlessly. The result is a multiply-connected flat space with no edges, potentially small enough that ancient light crosses it more than once. If that were the case, we might see repeated patterns in the microwave background. Pairs of matched circles with the same temperature fluctuations, rotated or mirrored, appearing at different positions on the sky. Researchers have searched for such signatures with modern CMB maps. So far, there is no clear detection of matched circles that would point to a small, wrapped topology. That absence of evidence does not rule out all compact shapes. It just tells us that if the universe wraps, the fundamental domain is likely larger than the observable region. In other words, the room we can see is too small to reveal the repeating wallpaper. Future datasets may tighten the constraints, but the main lesson remains. Geometry and topology are distinct. You can have a space that is flat like a table but connected like a hall of mirrors. Our observations place bounds. They do not exhaust the possibilities. Speculation about scale also reaches into how the universe began. Eternal inflation is one framework where inflation, the brief, rapid early expansion, doesn't end everywhere at once. It stops in pockets while continuing elsewhere, creating a multiverse of bubbles with potentially different physical parameters. In this scenario, our observable universe is a patch inside one bubble, and beyond our horizon, other bubbles exist with their own cosmic histories. This idea is difficult to test directly, but not beyond discussion. Researchers have proposed looking for telltale signatures in the CMB, such as circular anomalies from bubble collisions or statistically unusual patterns in large-scale structure. To date, surveys have not produced definitive evidence for such events, keeping the concept in the realm of motivated conjecture. There's a practical takeaway, even if bubbles never contact us. Whether the cosmos is infinite or just vastly larger than the observable part, our observational reach is bounded. The number 93 billion light-years across for the observable universe describes a comoving diameter today. The existence of a future horizon means that, as time passes, more of that expanse slips out of communicable range. The accessible set of galaxies shrinks. Physics places a horizon on what we can know empirically, and technological growth cannot breach a limit rooted in the structure of space-time. This limit has consequences. Astronomers building the far future record would rely on local relics to infer the past. The cosmic microwave background will redshift until it becomes undetectable against noise sources. Distant standard candles and rulers vanish from view. The clues we use now to recover the expansion history and the early conditions will fade. A distant civilization might infer a static or local universe if it lacked a preserved archive or a deep theoretical framework. That raises the stakes for the records we keep and the models we test today. On human timescales, though, we still have rich access. We can gather photons from the first few 100 million years after the hot Big Bang, measure polarization patterns in the microwave background to probe early physics, and map galaxy flows to weigh the dark sector. The horizon is not near enough to shut down inquiry. It simply defines a long-term boundary. Our task is to extract as much information as possible before natural redshift erases the farthest signals. Facing a possibly infinite space invites careful language. Infinity is not a measurement. It is a statement about unboundedness. Observations that support flatness open the door to infinite extent, but they do not require it. A flat, finite universe with a very large wraparound scale could look indistinguishable from an infinite one within our observable volume. Searches for non-trivial topology are the way to test that. So far, the sky looks consistent with a space that is either truly endless or so large that its repetitions, if any, lie beyond our sight. Meanwhile, the notion of galaxies leaving our horizon reframes how we talk about distance and time. Distance in cosmology is not one number. Light travel time tells us how long a photon has been in flight. Co-moving distance tracks where an object would be today if you could pause expansion and lay down a ruler. Proper distance changes as space changes. Horizons are statements about what signals can arrive given the full expansion history. This is why a galaxy can be 30 billion light-years away in co-moving terms and still be visible now, and also why, in the future, that same galaxy's newer light will never reach us. The asymmetry here is worth pausing on. We will keep receiving old light from galaxies that are already beyond the future event horizon, but only the light they emitted before crossing that causal threshold. No new information from them will ever be added to our sky after a certain time. The film keeps playing, but the studio has shut down production. The credits roll slowly as the last photons dribble in, stretched and cooled by expansion. None of this implies that meaning recedes with the galaxies. Limits frame knowledge. They do not erase it. By knowing the horizon exists, we learn which questions are answerable and which require new strategies. We can focus on the physics that governs the local structure we will keep, strengthen the connections between theory and the finite data we possess, and preserve the evidence that future observers will need. The shrinking of the accessible universe shifts emphasis to depth over breadth. It directs attention to the richness of the neighborhood that remains. So the answer to the opening question is quiet but firm. Galaxies slip away when the universe's expansion outruns the paths their light could take toward us. Some will never send a new photon our way again. Our local group will endure as a bound system, a long-term anchor in an ocean whose distant shores fade from view. The large-scale geometry looks flat, which allows for an unlimited expanse, yet the pattern of space could still loop back without our current instruments catching it. Searches for wrapped topologies continue. Matched circles in the microwave background have not appeared. Ideas like eternal inflation sketch a larger context beyond our horizon and motivate careful tests, but they remain speculative without clear signatures. The mini payoff is simple. The universe might be far larger than the part we can access, perhaps without end, yet our reach has a hard boundary that grows tighter with time. That boundary is not a defeat. It's the canvas edge that makes the image legible. With scale in view, the next step is not about how far we can see, but how the vastness we can't reach changes the way we think and feel about the small world we share. Small can feel like a verdict. Each time our map shrank us, from Earth at the center, to the Sun at the center, to the Milky Way as one galaxy among countless others. It felt like a step down the ladder, yet the drop never landed where people feared. Each demotion widened the frame and, strangely, made the view richer. The night became less about our place in it and more about how far our questions could reach. That shift is quiet and practical. When you let go of being central, you start looking carefully. Careful attention builds meaning. Those shifts didn't arrive as slogans. They showed up as better tools and better habits. The geocentric world gave way because measurements of planetary paths demanded a neater model. Later, the leap beyond the Milky Way came from a single star's rhythm and a telescope's patience. None of that erased human purpose. It redirected it. Purpose moved from a claim about status to a commitment to inquiry. When you realize you're not the stage, you get to focus on the play. Feeling small can trigger a reflex. If we are a speck, Do our choices matter? That's an understandable reaction to the numbers. Light years dwarf lifetimes. Galaxies multiply. Epochs roll past like weather, but the scale that shrinks us physically can expand us intellectually. Awareness grows when the map grows. It's like switching on more of the dashboard. You don't control the engine by being large. You control it by reading the gauges. Curiosity becomes the steady hand that keeps the system from drifting. There's a practical payoff to that mindset. When people adopt a wider view, they weigh consequences across longer timelines. You can see this in how we think about climate, species loss, and the thin layer of air and water that keeps us alive. The more we know about the starkness of other worlds, the more our atmosphere looks like a rare exception, not a background default. Knowledge lifts obligation out of mood and into method. Stewardship stops being sentimental and starts being strategic. The cosmic perspective turns out to be less about grand feelings and more about clear constraints. Space is vast, but habitability is narrow. Stars are common but stable, long-lived stars with planets in temperate zones, protected by magnetic fields and not constantly sterilized by radiation, are not guaranteed. Oceans require a delicate balance of heat and chemistry. Photosynthesis needs steady light and trace elements. Civilization needs a quiet enough environment to develop tools over many generations. You can count those conditions, not just marvel at them. That count directs hope, not despair. If the Milky Way holds hundreds of billions of stars, and a fraction of those host planets in zones where liquid water can exist, then some subset of galaxies beyond ours likely host their own cycles of geology, chemistry, and maybe biology. We don't need certainty to pursue the search. We need parameters. Drake-style reasoning, breaking the question into rates and probabilities, helps us identify where to look and what signatures to seek. Extend that logic beyond our galaxy, and the numbers get large enough to keep the search busy for centuries. Hope works best when it's tethered to evidence. We already see organic molecules in interstellar clouds, complex chemistry on icy moons, and exoplanet atmospheres that hint at varied compositions. None of this proves life elsewhere, but it lowers the barrier from fantasy to hypothesis. The point is less to declare that life must be common, and more to accept that the testable space is large. Being a small species in a large arena gives us the patience to run long experiments. The same perspective reframes ethics. When a crew finally sees Earth from a distance, the borders vanish and the physical finitude stands out. That sight, even second-hand, compresses arguments about policy into the basic reality of a single closed system. It nudges politics toward ecological bookkeeping, inputs, outputs, cycles, limits. All has a role here, but it's the kind you can schedule. You put a telescope in orbit, you point it, and you let the data calibrate your humility. Moments of collective seeing helped. A photograph of Earth against darkness, or a view of a small blue dot among bands of light didn't supply new physics, they offered a shared reference. Suddenly, billions of people had the same visual to anchor a feeling that had floated untethered. That anchor allowed a more grounded kind of care. It gave teachers, lawmakers, and kids the same picture to point at when they talked about air quality, water cycles, and the thinness of the biosphere. This perspective also reduces performative despair. Saying, "we are nothing," sounds deep, but it skips the math. On a cosmic scale, our mass and our reach are tiny. On a human scale, a single policy can save a river, a vaccine can save millions, and a mission can safeguard a planet from an asteroid. Scale is not a verdict, it's a unit conversion. You choose the yardstick that matches the task. That's not evasion, it's competence. Fragility, taken seriously, sharpens priorities. Finite resources and finite time push us toward projects with compounding returns. Education, basic research, infrastructure, prevention. The wider the universe, the more rare a stable corner of it looks, and the more sense it makes to keep that corner in working order. Fragility invites better engineering, not resignation. Being one of billions of galaxies doesn't weaken the case for care. It strengthens it by removing illusions of backup worlds on demand. There's another benefit to feeling small. It cools the ego enough to hear faint signals. Grandiosity is loud and impatient. Discovery rewards quiet and repeatability. The search for life, for new physics, or for subtle climate trends depends on attention to weak patterns across time. A large universe gives you time and space for that work. A small self gives you the patience to accept null results and try again. The combination is productive, not bleak. Meaning, under this view, stops depending on cosmic endorsement. It is built in layers, the meaning of a craft well practiced, the meaning of a relationship tended, the meaning of a question pursued until the data push back, the meaning of leaving a system healthier than you found it. None of these require that the universe notice you. They benefit from the fact that you notice the universe. Wonder and responsibility turn out to be a matched set. The same habit that looks up and asks how old a star is also looks down and asks how stable a watershed is. The same patience that waits for a faint galaxy to emerge from noise also waits for a social policy to show outcomes. Curiosity trains discipline. Discipline makes care effective. It's not a leap from a telescope to a water filter. It's a straight line. Extend the question of life to other galaxies and the stakes broaden without blurring. If biosignatures turn up in a nearby exoplanet's light, we'll ask how common they are in other star populations. Do spiral arms foster more long-term stability than elliptical halos? Do metallicity gradients across a galaxy change the odds of complex chemistry? Do interactions in crowded clusters sterilize or stimulate? Each answer refines where we look next, pushing the search out of our neighborhood and into the broader city. Meanwhile, our future unfolds on two tracks. One is local and practical. Keep this planet stable, shield it from known hazards, and manage our own systems with a long view. The other is exploratory. Build detectors, send probes, develop propulsion incrementally, and learn to use the energy we have without boiling the nest ambition stays, but it gets disciplined by physics. We can become a spacefaring species only by becoming a better Earth-faring one first. That mix of realism and reach makes the universe feel more intimate, not more remote. As the map spreads out, it fills with places that matter to us because we can study them and, occasionally, touch them. Knowing the distances doesn't push us away. It makes every photon that arrives a visitor from a specific street and time. The night sky becomes a ledger of relationships, not an empty waste. So smallness stops being a sentence and becomes a setting. Scale becomes another parameter to work within, like temperature or budget. You trade grandeur for grip. You trade center stage for a better seat in the audience, with a clear view and a good notebook. And that's enough. Because the work itself, the measuring, the caring, the asking, is where meaning accumulates. In that sense, the universe is not a cold verdict, but a generous context. It gives us room to be careful. It gives us examples of stability and catastrophe to learn from. It gives us horizons that move as we walk toward them, which is a decent description of progress. We don't need to own the stage to have a role. We just need to keep reading the light and minding the home that lets us read it at all. Which brings the story back to the map that keeps unfolding. From a milky band over our heads to a foam of galaxies stretching to a horizon defined by time. The scale that once felt like a threat turned into a tool, and the quiet habit of following evidence redrew the boundaries of what we call home. Next comes the step that ties those boundaries together, the way a single galaxy taught us to measure a cosmos and to live wisely within it. One star's steady rhythm pried open the ceiling we mistook for the sky, and somehow it made the ground under our feet feel steadier. A measured pulse in Andromeda became a new scale for reality, and with that scale in hand, our home didn't shrink. It gained context. The Milky Way's arms, our offset seat near the Orion spur, the dark halo that holds our stars in their wide circular glide. These details don't make us small in a dismissive way. They outline the neighborhood we can actually name, the part of the map we can defend and understand. A universe that grew larger gave our address sharper meaning. That clarity comes with a responsibility that doesn't need rhetoric. All our stories, languages, migrations, and arguments ride on a thin biosphere wrapped around a single planet. We can resolve star motions at the galactic center and trace filaments out to the horizon of the observable universe. Yet every breath depends on local air, local water, local soil. So we do the grounded work. We reduce what we waste. We guard the climate record and keep building it with better satellites and sensors. We protect the species that hold ecosystems together. We fund observatories carefully and share the data widely. Learning to read the sky with patience goes hand in hand with caring for the only world our hands can reach. Patience matters because the signals we seek aren't always loud. A faint dip in a star's light can reveal a world with clouds. A ripple in space-time can trace the last seconds of two black holes. A slight pattern in the cosmic background can refine how fast expansion accelerates. We miss these if we rush, or if we let cynicism set the pace. Science moved from the great debate to calibrated distances, from grainy plates to deep fields and redshift surveys, by tolerating uncertainty and tightening the screws, one measurement at a time. That ethic, applied to Earth and to the sky, is how we keep learning without burning what we stand on. There's a quiet kind of hope in that approach. The Andromeda Cepheid was not a roar. It was a consistent beat against a noisy background, checked, rechecked, and anchored to a ladder of methods that could fail and be fixed. That culture of correction is a model for more than astronomy. We can test policies like we test parallaxes. We can treat predictions like provisional fits to data, revised as new information arrives. Owning a mistake is only a problem if you hide it. So we hold both scales at once. We keep eyes on the horizon the cosmos allows, and we keep hands on the tasks that make life here durable. We invest in the instruments that extend our reach, from small backyard scopes to the next generation of space telescopes. We teach the curiosity that keeps looking up when answers are slow. We preserve dark skies. The Milky Way is a thing our children see with unaided eyes, not a story in a book. If one measured blink could open the sky, what quiet signal is waiting now, just below our threshold? A whisper in a transit curve, a slight wobble in a stellar spectrum, a new pattern in a background we thought we knew. Something modest, regular, and precise enough to widen the map again.